Welcome back to week 7 of our course, Introduction to Physics and Biophysics. Last week, we studied fluid mechanics, focusing on how physical laws govern the movement of liquids and their applications in the human body. This week, we move into another cornerstone of biophysics, temperature, heat, and thermodynamics. The lecture is divided into 2 parts. Part 1 teaches the foundational physics, what temperature and heat really are, and how the laws of thermodynamics govern energy flow. Part 2 is about how these physical principles apply directly to the human body and thermoregulation. By the end of Part 1, you will be able to differentiate between temperature and heat, describe the first law of thermodynamics, explain the biological meaning of delta U equals 0, energy equilibrium, identify and describe the 4 mechanisms of heat transfer, apply the second law of thermodynamics to heat flow in the human body. Understanding these concepts is crucial for comprehending the body's energetic balance and its interactions with the environment. Let's begin by differentiating between 2 fundamental terms, temperature and heat. While often used interchangeably, they represent distinct physical phenomena. Temperature is a measure of the average kinetic energy of the particles within a substance, indicating its degree of hotness or coldness. Heat, on the other hand, is the transfer of thermal energy between systems due to a temperature difference. Can you articulate the key difference between temperature, an intrinsic property, and heat, which describes energy in transit? Now, let's look into the first law of thermodynamics, a cornerstone of energy conservation, represented by the equation delta U equals Q minus W. Here, delta U signifies the change in the internal energy of a system. Q represents the heat added to the system, and W denotes the work done by the system. This means the energy of a system can be changed by adding or removing heat, or by doing work on it, or having it do work. How does this law connect the concepts of heat and energy transfer to what the body does? Specifically, what does a delta U of 0 mean for a system, and why is that important for maintaining a steady biological state? This state, where internal energy remains constant, is vital for maintaining physiological stability and function. In biological terms, Q, or heat, represents energy gained or lost through metabolism, environment, or food intake. Work, W, is energy the body uses for muscle contraction, nerve impulses, pumping blood, etc. The change in internal energy, delta U, reflects the overall energy balance within the body, influencing everything from body temperature to cellular processes. When delta U equals 0, it means the body's total internal energy remains constant. Energy entering equals energy leaving. So heat gained from metabolism or environment equals work done minus heat lost through skin, respiration, etc. The body is in energy equilibrium. It's not storing or losing energy overall. This condition is crucial for homeostasis, the body's ability to maintain stable internal conditions. Temperature stays near 37 degrees Celsius, 98.6 degrees Fahrenheit. Metabolic processes run efficiently. Cells function within narrow energy limits. If delta U is not equal to 0 for too long, positive delta U, energy in, is more than energy out, leads to overheating or energy storage, such as fever, fat gain. Negative delta U, energy out, is more than energy in, leads to cooling or energy deficit, like fatigue, hypothermia. The first law links heat and work to the body's internal energy. A delta U of 0 means energy balance, the foundation of physiological stability and health. Please note that the equation for the first law of thermodynamics can be written as delta U equals Q minus W, or delta U equals Q plus W, depending on the sign convention used for work. The form delta U equals Q minus W is common in physics and engineering, where W is the work done by the system. The form delta U equals Q plus W is common in chemistry, where W is work done on the system. Next, let's explore the 4 primary mechanisms of heat transfer: conduction, convection, radiation, and evaporation. Conduction is the transfer of heat through direct contact, like touching a cold surface. Convection involves heat transfer through the movement of fluids, such as air currents carrying heat away from the body. Radiation is the transfer of heat via electromagnetic waves, like the warmth felt from the sun or a fire. Evaporation is the cooling process that occurs when a liquid, such as sweat, changes into a gas, absorbing heat from the body. For a person standing still in a room, which of these heat transfer mechanisms do you think is dominant? The answer often depends on factors like air movement and ambient temperature, but convection and radiation play significant roles. Finally, let's consider the second law of thermodynamics. Heat always flows spontaneously from a region of higher temperature to a region of lower temperature, and that The total entropy, disorder, of an isolated system always increases in any natural process. In simpler terms, energy tends to spread out and become more evenly distributed. A hot object has faster moving molecules, higher kinetic energy. When it's placed near a colder object, some of that energy naturally transfers until both reach the same temperature, thermal equilibrium. Entropy, a measure of disorder or randomness, naturally tends to increase in isolated systems. How does this fundamental law explain why the human body spontaneously loses heat to a cooler environment? Because our body temperature is typically higher than the surrounding air, heat naturally dissipates outwards. This continuous heat loss is a direct consequence of the second law, driving the body to constantly generate heat to maintain its core temperature. By grasping how temperature, heat, and thermodynamics govern physiological processes, you can better appreciate the intricate balance of health. Thank you for joining this session. See you in part 2.